program with the first paper entitled Gas-Solid Virial Coefficients for Nitrogen and CO on Graphitized Carbon. The paper is submitted by Mary J. Bogden and William A. Steele from the Department of Chemistry at Penn State. The paper will be given by Mary Bogden.
Thank you.
I'll deal with that one.
Okay. Is that all, Stephen? Thank you. That's nice.
The purpose of this study was to measure the gas-solid virial coefficients of nitrogen and carbon monoxide on graphitized carbon. And then we compared these to values of the virial coefficients calculated using statistical mechanics. And by doing this, we want to gain some information about interaction potentials on the surface. The interactions we're specifically interested in are the gas-surface interaction, that is the interaction of a single gas molecule with the surface, and the gas-gas interaction, or the interaction of two adsorbed molecules with one another. The experiment that we do is a familiar one. We use a volumetric absorption apparatus, which consists of calibrated volumes, two pressure gauges, one which reads high pressures, and another one which reads pressures below 100 torr, and a sample cell which contains exfoliated graphite called graph oil, which is known to have a very homogeneous surface. The sample cell is maintained in a constant temperature bath so that over the course of an isotherm we can maintain our temperature to within plus or minus 0.06 Kelvin. In the experiment, we measure the number of moles of the gas absorbed on the graphite and the pressure which is in equilibrium with the absorbed gas at a constant temperature. And for the purposes of obtaining virial coefficients, what we want to do is concentrate on the high temperature, low pressure region of the isotherm. So to do this, we measured 8 isotherms each of carbon monoxide and nitrogen in the temperature range from 90 degrees to 210 Kelvin. And we concentrated on the low pressure, low coverage portion of the isotherm. This is a virial form of the isotherm equation, which is what we use to plot up our data. In this equation, B sub AS is the second gas-solid virial coefficient. B2D is the two-dimensional second virial coefficient. C2D is the two-dimensional third virial coefficient, and so on. A is the surface area. And this expression, if you see Na over A, is the surface density. So this is an expansion in surface density. Just like the regular three-dimensional virial coefficient is an expansion in the bulk density. This slide shows just a sample of our data plotted up in such a way as to take advantage of this isotherm equation. We plot ln of Na over P versus Na. And when we're at very low surface coverages, we can truncate this series after the second term, and we would expect at low coverages then that this would give us a straight line with a slope equal to minus B2D over A and an intercept equal to ln of BAS over KT. And that's how we extract these real coefficients from the experimental data. Then to calculate the virial coefficients, we use the expressions given by statistical mechanics. Now the second gas-solid virial coefficient is related only to the gas-solid potential. And the two-dimensional second virial coefficient, however, is a bit more complicated. It's related both to the gas-solid potential in terms of these G functions, which we have here, and it's related also to the gas-gas potential, which is given by this F function here. So in order to calculate those quantities, we need to specify some form for the potential. In the gas-solid potential, what we do is the gas-solid potential consists of the sum of the interaction of each atom of the molecule with each atom of the substrate. And then we specify the form of that interaction to the Leonard-Jones 612 interaction. Now, if we were to substitute this then into that equation for BAS, we would still have a very complicated function to evaluate. But it turns out that we can simplify this by expanding the potential in Fourier series. And since we are dealing at high temperatures, we can consider that our gas is a mobile gas on the surface, and this Fourier series can then be truncated after the first term. And this expression here is the first term of the Fourier series. And it contains two adjustable parameters, the epsilon GS, which is a well depth, and sigma GS, which is the distance of closest approach. It can be thought of something like a hard sphere collision diameter, although it's not necessarily equal to that value. The gas-gas potential contains two terms. We have a site-site interaction term and a quadrupolar interaction. The site-site term means we take into account the interaction of each atom of each molecule with one another, so that there's 4 interactions. And we again choose a Leonard-Jones 612 form for that interaction. And it contains two adjustable constants, the well depth and the distance of closest approach. For the quadrupolar interaction, what we do is we place partial charges on the atoms of the molecule, and at the center of mass we place partial charges equal to twice the charges placed on the atoms, but opposite in sign. We then calculate the Coulomb interaction between the charges on one molecule with the charges on the other molecule. And the quadrupole moment is then related to these partial charges according to this equation, where d sub I is the distance of the charge from the center of mass. Our next step is to fit our data to the theory to get values for those adjustable parameters which I indicated. This shows our data for nitrogen on graph oil. These squares are our data, and the line through it represents the theoretical curve. And as you can see, the data in theory fit quite well. And the values for the parameters that we obtain are given right here in this column. They agree quite well with the values obtained by Kuiper, Morrison, Peters, and Ozaki in a recent study that they did. They measured heats of absorption of nitrogen on graph oil at 79 Kelvin, and they fitted their data to the same potential form as we did, and their values agree within 3% with our values for the well depth. Also, in the recent molecular dynamic simulations, Talbot, Tildesley, and Steele used a value of 31.9 for their well depth, which they obtained by using the geometric combining laws, and our value lends good support to the value that they use, since these values are within 5% of one another. We also then fitted our carbon monoxide data to the same potential, and we find that again, the circles are our data and the line is the theoretical curve. If you look at the table here, we can see that the values for carbon monoxide and nitrogen don't differ by all that much. This value for carbon monoxide is roughly 10% larger than that of nitrogen, which shows that carbon monoxide is attracted a little bit more strongly to the surface than nitrogen, but this is not a really large difference. And again, the value for the sigma GS is just a little bit smaller, again indicating that it's attracted a little more strongly to the surface. Now, since the B2D is related to both the gas-solid and the gas-gas potential, it would give us too many parameters to be trying to evaluate if we attempted to fit our B2Ds and evaluate all the parameters based on that alone. So we use these values as the values for the gas-solid parameter in our calculation of B2D, which leaves us only the gas-gas parameters then to fit when we fit the data to theory. This slide shows our data for nitrogen on graph oil. This plot is B2D versus 1 over T. And our data is represented by these bars here. These squares are the data of Levy and Perotti obtained several years back They did their experiment on a slightly different surface. However, it is a homogeneous graphite surface, and we would still expect their results to be comparable to ours, and indeed, their data fits ours quite well. Now, in calculating values of B2D, we had to do somewhat of a trial and error kind of a process. And what we did was we began by using the values that Talbot et al. Used in their molecular dynamic simulations for the parameters. These values are known to reproduce the bulk nitrogen experimental data quite well. But as you can see, it doesn't reproduce our data very well at all. In fact, the results that reproduce our data are given here, and this well depth is roughly 25% lower than this value here. And this value for Q effective gives a quadrupole moment, which is roughly 20% lower than the experimental quadrupole moment. This is not really a surprising result, since we would expect the substrate to have some effect on the lateral interactions of the molecule. And indeed, investigators have shown that substrate-mediated effects can produce a reduction in the lateral interactions by up to 20% on the surface. Now, turning to carbon monoxide, when we first began our work, our fitting process, we started using an atom-atom potential that was proposed by Mirsky. This potential takes into account the asymmetry of carbon monoxide. However, it did not reproduce our B2D values at all, and so we chose to use a symmetric nitrogen-like potential, that's the one that I have already described, in fitting the data to the theory. Now, this may sound a little bit unusual, but in these investigations, these people ended up using symmetric nitrogen-like potentials as well when trying to, in their calculations, when they tried to fit the available experimental data to their calculations. So we're not the only ones who go with this approach. The reasons why we would even have thought to do this can be seen when we compare some of the properties of nitrogen and carbon monoxide. If we look first at the electron energy contour diagram shown here, this outer contour for both of these, within this contour, 95% of the charge of the electron is contained within those contours. And these contours are very nearly the same for carbon monoxide and nitrogen. And this is probably what gives rise to the fact that many of the properties of these molecules are very nearly the same. And that's indicated by the fact that the ratio of their properties is very nearly equal to 1. And this is true for both the bulk phases and for properties in two dimensions, or the adsorbed phase. Now, if we look at the inner contour of carbon monoxide, we can see that that's asymmetric, and that's probably what gives rise to its very small dipole moment and its larger quadrupole moment. In fact, the quadrupole moment of carbon monoxide is 20 to 40% larger than the dipole moment of nitrogen. And we would expect that difference in quadrupole moments to have some effect on the properties of two molecules. And indeed, that's definitely true. If, for example, we look at the bulk virial coefficients of nitrogen and carbon monoxide, these circles represent the experimental data for bulk virial coefficients for nitrogen. The squares are data for bulk virial coefficients for carbon monoxide. And the lines through here are curves that we calculated for the virial coefficients using the nitrogen-like potential I described, and these values for the parameters. We used identical values for the well depth and the distance of closest approach for both nitrogen and carbon monoxide. The only difference in these curves comes in the effective charge that we used. And we used a charge that would for carbon monoxide that would reproduce its quadrupole moment. And you can see that using a different quadrupole moment effectively reproduces the experimental virial coefficients. So then we would expect that in two dimensions that the same kind of thing might result, that the difference in the quadrupole moment would explain the difference in the two-dimensional virial coefficients. Well, this doesn't turn out to be the case. The squares here are our experimental carbon monoxide data, the circles are the nitrogen data, and here we have the best fit values for the parameters. The well depths and the sigma values are virtually identical for nitrogen and carbon monoxide, just as in the case for the bulk virial coefficients. However, the surprising result is that the quadrupole moment for both is identical as well, rather than being scaled by the quadrupole moment as was the case for the bulk data. So what conclusions do we draw? Well, there's a reduction in the gas-gas potential for both nitrogen and carbon monoxide relative to the potential for the bulk gas. And as I indicated earlier, this is probably due to substrate-mediated effects. However, for carbon monoxide, the reduction in the quadrupole moment that's needed to produce agreement between theory and experiment is much larger than would be expected. And the values for the potential parameters are very nearly the same as those for nitrogen. The recent studies by Morishega et al. Doing X-ray diffraction and the heat capacity studies by Feng and Chan of the in-plane orientational order disorder transition on the surface tend to support these results, however. They have found that the transition in 2 dimensions, this order disorder transition, for carbon monoxide occurs at almost the same temperature as the transition for nitrogen. And it was expected that this temperature would be maybe as much as twice the value, since if you look at the analogous transition for the bulk, the alpha-beta transition, you find that the ratio of those transition temperatures is 1.73. And we would have expected a similar ratio for this order-disorder transition, and that's not the case. So this reduction in the quadrupole moment of carbon monoxide on the surface is a bit unexpected, and we don't really have a complete explanation for it, but we hope that with further investigations that some light can be shed on this problem. Thank you.
Paper is now open for discussion. I wonder, then if I could ask one question, and that has to do with, is there a quantum mechanical theory that has been worked out for the reduction expected in the quadrupole interactions, pair quadrupole interactions, as a result of being in the potential of the solid? There isn't for dispersion forces.
I think, I'm not that familiar with this, but I believe the McLaughlin energy is somewhat of a working in that direction. However, it doesn't tend to take into account as completely the reduction. It would account for, say, a 20% reduction, but not as much as a 50% reduction, which is what we seem to be seeing. And again, we see a reduction in the nitrogen quadrupole moment, but we see so much greater of a reduction in the carbon monoxide moment, so that the substrate-mediated effects of the McLaughlin energy can explain it to a certain extent, but it doesn't appear to be adequately explaining it.
Very briefly, when this is graphite material, is it in powder form or is it in a sheet form or what?
Graphite is in a sheet form. It's made from graphite foam, which is this big block of, they kind of puff up the graphite and you get a big block, and then they take it and roll it out flat. And then we just cut it into little circles to fit into our sample cells, stack them up.
Now the next question related to that, what is the absorption capacity in terms of classical BET surface area or?
The surface area, the BET surface area is over 1,000 meters squared per gram in the sample. Is that what you're asking?
That's what I was asking.
Yeah, we use a very large surface area.
Which makes me look at Duke's law, what you talked about. From the standpoint of 1,000 square meters per gram means that your wall thickness is only probably about 2 molecules thick. And in doing so, how much can you assume that the substrate is inert to this force of absorption? At 1,000 square meters per gram, you're spread out like a model, which you spread that out. It would only be about 4 carbon atoms thick. And in doing so, I'm a little dubious about utilizing the theory using which you assume that you've got one field there of an inert solid substrate.
I don't think so, because, well, I'm not sure if I understand what you're saying, but, you know, the graph foil has a density of, it has about 20 meters squared per gram. That's not like it really isn't all that, although our surface area is large only because we have such a huge volume. we have like 50 grams of the
Oh,
graphite.
I'm sorry, you said you had 1,000 square meters or 1,000 square meters?
I have 1,000 meters squared, but not per gram.
Oh,
No,
sorry.
I have about 20 meters squared per gram. I have that on one of the slides back here. It's,
All right.
yeah, I'm sorry. I'm sorry. Yeah, it's 50 grams of this stuff. We have a lot of it.
They produce this graph oil, if I'm correct, with the use of some oxidizing acid like nitric acid or sulfuric acid that causes puffing. Do you know if there was any oxygen on the carbon surface at all?
We don't know ourselves from doing an actual analysis. However, I think usually what they use in this process, there have been studies that have been done, like for example by Bergeno, have shown that this surface is very homogeneous, so that the only kind of oxygen you'd expect on the surface would be at the edges of the basal planes. Those would be the only pore sites or strong sites that you'd find on there. And so probably there's not all that much oxygen except again at the edges of the basal planes.